Myself Soumya BJ, Assistant Professor, Department of ECE, SJBIT. The subject is Basic Electronics. Subject code is 18 ELN 14/24. In this session, I'll be starting with Module 4. It is about BJT applications, feedback amplifiers, and oscillators. The textbooks that are to be referred for this subject are Basic Electronics by D.P. Kothari, I.J. Nagrath, Electronic Devices by Thomas L. Floyd. The contents that are being discussed in this module are BJT as an amplifier, BJT as a switch, transistor switch circuit to switch on off an LED and a lamp in a power circuit using relay, feedback amplifiers, their principal properties and advantages of negative feedback, as well as types of feedback, and in particular voltage series feedback amplifier will be discussed, as well gain stability with feedback, oscillators, the principle of operation, the Barkerson criteria for oscillation, RC phase shift oscillator, Wien bridge oscillator, IC 555 timer, A-stable oscillator using IC 555 timer. These are the topics that will be discussed in this particular module 4. Let us start this session with the first topic, bipolar junction transistor, their applications as an amplifier and a switch. The bipolar junction transistor, or simply we call it as BJT. It is a 3-layer, 3-terminal and 2-junction semiconductor device. In the previous sessions, we have understood about a 2-layer 1-junction semiconductor device, which we call it as a diode. The diode is made up of P and N type material. So we tell that it has got 2 layers and 1 junction. It is a semiconductor device because it is made up of P and N type material. This device we call it as a diode. Now currently we are discussing about a transistor which is a combination of 2 back-to-back diodes. 2 back-to-back diodes provided crystal continuity to be maintained. Addition of another layer in this BJT results in a 3-layer 2 junctions device which has NPN or PNP form and is called as a transistor. With a terminal connected to each layer, it acts as a 2-port device and one of the terminals is connected between the 2 ports. Such a transistor we call it as a BJT, bipolar junction transistor. It acts as a current controlled device with the output current which is being controlled by the input current, and it is such that the input current waveform will be replicated at the output. This is the amplifying action of the transistor which is commonly applied in various types of audio or video amplifiers. And this BJT can also be made to act as a switch where the input current level controls the on-off state of the output current. This mode of operation of the BJT finds wide applications in high-speed digital electronics. In many of the applications, these transistors are used for 2 basic functions such as switching and amplification. Why the name bipolar is being included in this bipolar junction transistor is there are 2 types of charge carriers which are involved in the working of the BJT. Whereas when we discussed about FET, we called those devices as unipolar devices because in FET the conduction was only due to one type of charge carriers. But in BJT, it is due to 2 types of charge carriers. That is why they are called as bipolar junction transistor. These 2 charge carriers are holes and electrons. As we know, the holes are positive charge carriers and the electrons are negative charge carriers. The bipolar junction transistors are of 2 types. The 2 types are mentioned as NPN and PNP. The functioning of both the transistors is same, but actually they differ in terms of biasing as well as the power supply polarity. In a PNP transistor, between two p-type materials, n-type material will be sandwiched. Whereas in case of NPN transistor, the p-type material will be sandwiched between two n-type materials. If I take a PNP transistor, two p-type materials will be sandwiched between a n-type material. In the NPN transistor, two n-type materials will be sandwiched between the p-type material. And these two transistors can be configured into many types like common emitter, common collector and common base configurations. Now from this PNP and NPN materials that are being used in this PNP as well as NPN transistor, we take three terminals. Those three terminals are mentioned as emitter, collector and base. Emitter, collector and base. Here the n-type material becomes the emitter, which is present on the left hand side. The n-type material on the right hand side becomes the collector. The p-type material in the middle becomes the base. Similarly, for the PNP transistor, the p-type material on the left hand side will be the emitter. The p-type material on the right hand side will be the collector. The n-type material in the middle will be the base. Correspondingly, the symbol, as you can see, it is been displayed in this last slide for both NPN and PNP transistor. Three terminals are being represented in this symbol of this NPN and PNP transistor. The symbol of these two transistors vary with respect to the arrowhead representation. The arrowhead representation, as we know, it indicates the conventional current direction. The current direction is usually represented by means of the arrowhead symbol, which is present at the emitter terminal. In the NPN transistor, the arrowhead symbol will be towards the emitter terminal. It is away from the transistor. Whereas in the PNP transistor, the arrow mark symbol will be towards the transistor. At the emitter, the arrow mark symbol will be towards the transistor. It is representing as flowing into the transistor. In the NPN transistor, it is away from the transistor. It is flowing towards the emitter from the collector as well as the base terminals. This differentiates between the NPN and PNP transistor symbols. Now let us take an NPN transistor and let us analyze its working with respect to one of the configuration, which we call it as common base configuration. In the common base configuration, the base terminal becomes common for both the emitter and the collector terminal. The circuit, as you can see in this slide, here the base terminal is common to the emitter as well as the collector. Okay, this is the NPN transistor. This NPN transistor has got the p-type material in the middle, the two n-type materials on the opposite sides. It means the n-type materials are sandwiched between a p-type material. In the n-type material, the electrons are majority charge carriers, and in the p-type material, holes are majority charge carriers. Now to this NPN transistor, we have done the connection in such a way that the base becomes common for both the emitter and the collector, and there is a biasing that is being applied to this NPN transistor such that there is a positive terminal, positive biasing connected to the base terminal and negative biasing connected to the emitter terminal. That is one biasing voltage between emitter and base. Similarly, one more biasing voltage is between collector and the base, which is positive towards the collector and negative towards the emitter. In this, as you know, NP becomes, N is the emitter and P is the base. Okay, when N is given a negative voltage and P is given a positive voltage, as you know, this junction now becomes forward biased. So, EB junction is forward biased. And what about the PN junction? P is negative and N is positive. So this becomes now reverse biased. Since the base emitter junction is forward biased and the collector base junction is reverse biased, all the carriers that are injected into the emitter, are swept away through the base into the collector. The carriers that are being injected into the emitter are swept away through the base to the collector. As a result, we can tell that the equation IC is equal to alpha into IE. For alpha is equal to 1, the IC is equal to IE, because most of the carriers from the emitter, they reach the collector. So the current at the emitter is almost equal to the current at the collector. Now the characteristics of this NPN transistor can be represented for both input and output, and they are called as input and output characteristics. The input characteristics is the graph of VBE versus IB. VBE versus IB. VBE is taken on the x-axis and IB is taken on the y-axis. In this graph, as we can see, there is a constant value VC that is being taken, and for the increasing value of VBE, the current IB increases. Okay, and as this VC voltage, which is kept constant, increases, we can see that there is a reduction in the current carrying capacity. Now there is one more characteristics that is being displayed in the slide. This we call it as output characteristic. In this output characteristic, the VCE is plotted against IC. The VCE is the collector to emitter voltage and IC is the collector current, which is in the order of milliamps. For various values of IB, this output characteristics, which can also be called as collector characteristics, is being plotted. Okay, there are regions of consideration in this diagram. 3 regions I need to consider in this diagram. One is active region, one more is saturation region, the other one is cutoff region. Okay, in the active region, there is a linear value of change in the current with respect to the collector to emitter voltage. This can also be called as a linear region in which the amplifying action of the circuit takes place. Now moving on to the saturation region. The saturation region is the region in which we can tell that both base emitter and collector base junctions are forward biased. So this region is been written on the left of this characteristic diagram. In this region, the collector current rises exponentially to the value that is being set, and it is the region in which the value is told to be saturating at a fixed value. It is maintaining a fixed value. It is saturating at a constant value. That is why it is called as a saturation region. One more region we call it as cutoff region. In this region, both base emitter and collector base junctions will be reverse biased. As a result, we tell that IE value is equal to 0 and IC value is also equal to 0, because both the junctions are reverse biased, means there is no current conduction taking place. So IE is 0 as well as IC is also equal to 0. Now for different values of IB, the characteristic diagram is been plotted for different constant values of IB. As we can see, as IB decreases in the value, the current conduction decreases and it almost becomes equal to 0. As we can see here, as IB value is decreasing from 60 microamps to 10 microamps, the collector current, that is the output current, is nearly almost approaching the 0 value, and at IB is equal to 0, the current value is also equal to 0. It means the current value is more the output current is more whenever the input current is also more. Whenever IB, that is the input current, increases, the output current IC also increases in value. Now let us discuss about the applications of the BJT. Let us first start with the first application in which BJT is acting as an amplifier. Let me first tell you what is amplification. The amplification is the process of linearly increasing the amplitude of an electrical signal. Amplification is the process of linearly increasing the amplitude of an electrical signal. It is a process by which a weak signal is converted into a strong signal. A signal which is having lesser amplitude will be converted into a signal which is having higher amplitude. A weak signal is converted to a strong signal. It means here we are increasing the amplitude of the electrical signal, and this becomes one of the major properties of the transistor. And here whenever we tell BJT, it is a current control device and we are dealing with this current gain, and we tell that its current gain, which is represented as beta, is very much greater than 1. And a BJT, as we come across to the characteristics just now, when it is biased in the active or the linear region, we tell that there is more current. It means why there is a current conduction taking place, because the BE junction is as a low resistance since it is forward biased, and the CB junction as a high resistance due to the reverse biasing. Whenever the BE junction has low resistance and it is forward biased, the current conduction is been taking place. The carriers are moving from emitter towards the collector, due to which there is a current conduction, and we tell that collector current IC is almost equal to IE, and that region of conduction we call it as active region or the linear region. Now let us analyze the amplification process of the BJT. Already we discussed about the current equations. We know that IE value is equal to IC, and IE can be totally written as equal to IC plus IB, but since IB is very much less than IE, I can tell that IE is almost equal to IC. IE is almost equal to IC. Now this is the current equation of the BJT, which is telling that the current gain is very high. The current gain is very high. Now let us discuss how amplification is taking place in the BJT. Let us consider first an AC voltage. Let us consider first an AC voltage here. Let us represent that AC voltage as Vs. Okay, this AC voltage is being amplified. It has to be amplified, and as we can see, it is being superimposed on the DC bias voltage VBB. This is being superimposed on the DC bias voltage VBB. Okay, and this VBB is connected in series with the base resistor RB according to the circuit diagram. The DC bias voltage VCC is being connected to the collector through the collector resistor RC. The DC bias voltage VCC is connected to the collector through the collector resistor RC. Here the AC input voltage which we are calling as Vs, it produces a AC base current which results in a much larger AC voltage across the RC, which is being amplified as well as it is being inverted. The AC input voltage Vs, it produces a AC base current which results in a very much larger AC voltage across the RC, which is being amplified as well as inverted. The AC input voltage Vs produces a AC base current IB, which results in what? A AC voltage across RC, which is nothing but the output voltage. This is the AC voltage across RC, which is nothing but the collector voltage. This collector voltage is amplified as well as it is been inverted. It is a amplified and inverted version of the AC input voltage. Now let us discuss this analysis by just considering a AC equivalent circuit. Let us first write the AC equivalent circuit. This is my AC equivalent circuit. Okay, in this circuit, as we can see, this AC equivalent circuit is represented by making DC bias sources equal to 0. It means I am getting this circuit by making DC bias sources VBB is equal to 0 and VCC equal to 0. And whenever I tell the AC value, the AC values are usually represented with the suffix in small letters. It means if I write the base current, capital R with a small b represents the base resistance of the AC equivalent circuit. Similarly, capital R with a small c represents the collector resistance. Similarly, I can write the base voltage as capital V with the suffix B, and the current that is flowing into the base terminal, I will write it as capital I with a small b, that is a base AC base current. Similarly, capital I with small c, that is AC collector current, and capital I with a small e, AC emitter current, and the total output across the collector terminal, we call it as capital V with a suffix C. This is the collector voltage. Now let us okay, this again I have written VC, so I will just remove this VC now. Fine. Now let us do the analysis and derive the expression and justify that the amplification is been taking place by the help of the BJT. Now in this characteristic diagram, the forward biased base emitter junction, it exhibits a very low resistance to the AC signal V in, and this internal AC emitter resistance we designate it as RE bar. Let us designate this internal AC emitter resistance as RE bar. Now we can write the AC emitter current as IE. This IE is almost equal to IC, and this can be written as equivalent to the voltage by the resistance. Here which voltage I need to consider? The base voltage. So VB divided by the resistance. The resistance will be the AC emitter resistance RE bar. Let us take this as equation number 1. Now the AC collector voltage will be VC is equal to IC into RC. IC into RC. This can also be written as IE into RC. This becomes my equation number 2. And also we have VB is equal to V in minus IB into RB. According to the circuit diagram, I can take the VB value as equivalent to VB equal to V in minus IB into RB. V in minus IB into RB results in VB. Now, if I consider the VB and VC, if I consider VB and VC as the transistor AC input voltage and transistor AC output voltage, VB is AC input voltage and VB is AC output voltage. Now let us write the voltage gain, which is the ratio of VC to VB. The voltage gain AV is equal to output voltage by input voltage. Which is output voltage here? VC. Which is input voltage? VB. So AC is equal to VC by VB. Now from equations 1 and 2, 1 and 2. If we do the substitution, AV will be equal to IE into RC divided by VB will be equal to IE into RE bar. This in turn results in the voltage gain AV equal to RC divided by RE bar. AV is equal to RC divided by RE bar. Now in this expression, the RC is very much greater than the AC emitter resistance. So the output voltage is always greater than the input voltage. So what is the justification that we can get from this? It means the VC is amplified version of VB. VC is amplified version of VB. It means the amplification has been done for the input voltage VB and we have got the output voltage VC. Now let us continue our analysis with respect to the current gain. Now we discussed about the voltage gain and we came to the conclusion that the input voltage is being amplified. Now let us discuss with respect to the current gain. How do I write current gain? It is represented as AI. AI is equal to what? IC divided by IB. That is equivalent to the current gain factor. The gain factor beta. It is the current gain, collector to base current gain beta. Now we know that IC is very much greater than IB. Since IC is very much greater than IB, AI is very large, means the current gain is very large. So we tell that the amplification has taken place. Now similarly, let us continue this discussion with respect to the power gain AP. The power gain AP is the product of voltage gain AV and the current gain AI. The power gain AP is the product of the voltage gain AV and the current gain AI. Since voltage gain is high and the current gain is high, we can tell that the power gain is also very high. Hence, we can finally justify that the BJT is acting as an amplifier. Right now, we discussed about the first application of the BJT, that is amplification. In the next session, we will continue with the second application, that is BJT acting as a switch. This is the bibliography of the subject. Thank you.